How we doing, guys? I wanted to give you a video to help you out with the second free response question you had for homework from Wednesday, 3/18. This one, like I said, is pretty darn close to the one that you did or that we did in class that I did on the other video. Some elements of it are pretty much exactly the same, and then there's a few different pieces that are unique to this problem. So I want to go over those specifically. So let's jump into it. This scenario, and again, I talked about trying to visualize exactly what's happening, and I think that gives, I think it just makes it easier to deal with these functions that aren't so nice. They look definitely a little bit more complicated than some of the things we're used to working with, and so just being able to visualize sort of what's happening, if this was a real world, real life scenario, I think just makes it easier to get through and maybe makes the questions a little bit more manageable. So this one, we've got this drain pipes, all right? So water's going to this drain pipe. It's raining outside. You've got this drain pipe. Think of like a gutter or something on the side of your house, maybe. And so rainwater is flowing into this drain pipe. We know the rate at which water is flowing in, which is R of T. All right, so that's water going in feet per hour. Remember, we talked about noting the units, so feet per hour, and T is measured in hours, and I have a specific interval from 0 to 8. Okay. One thing I noticed right off the bat is that T equals 0 is the time it starts raining. Right. I know this is at the end of the question, but we talked about trying to find this right away. All right. There are already 30 cubic feet of water in the pipe at time T equals 0. All right, which means either for whatever reason there's water left in there, or we're picking up this function in sort of the middle of the rainstorm, right? So T equals 0 isn't necessarily the time it starts raining. It's just a time in which you started tracking water going into the pipe. And so that's what this rate is for, right? So initial value, T equals 30 cubic feet of water. Okay, if you want to write that sort of on the side somewhere, or just kind of underline it or note it or circle it in the problem, that kind of strategy is really helpful to remind yourself that you're probably going to have to use this in some way throughout the problem. Might not be right away, but probably eventually. Okay. All right. So then the second part of the problem is talking about, well, now we've got the other end of the pipe, right? So the water is going into the pipe from one end, and at the other end of the pipe, it's actually partially blocked. Okay. When I first read this question, I thought about, again, it's raining outside. I've got this gutter that's going into a drain pipe onto your lawn, and at the other end of that drain pipe, maybe there's like some leaves or grass or something there that's sort of blocking the water from flowing out nicely and smoothly. And so that's why we've got this like good visual of the pipe being blocked. And so my second model is the rate at which water is being drained, or the rate at which water is leaving the pipe. Okay, so comparing it to our banana problem, right? R of T is similar to bananas being put on to the display table, and D of T is similar to bananas being taken off of the display table. So they're flipped in terms of when they were introduced to you because of the scenario that you're working with. But in terms of, hey, R of T is like an accumulation, and D of T is sort of a dissipation of sorts where water is leaving the pipe. Okay, and so this is cubic feet per hour as well, so which is nice. So the two units match up. They're both from 0 to 8, which again is important because if we have to figure out a total accumulation function, since now these two intervals are exactly the same, I probably just need one integral as compared to two integrals, which is what we did for the banana problem. All right, so for part A, this one is really similar to part A from the last question, almost identical in nature. It says, how many cubic feet of rainwater flow into the pipe during the 8-hour time interval? Hey, I know the rate at which it's going in. I know that the integral is going to accumulate or tell me the sum of all of the rain that was flowed into that pipe over the 8-hour period. So I'm just going to take the integral from 0 to 8 of my R of T, the rate at which water is going in, and get my answer. All right. Again, just a quick reminder, this is a calculator active problem. So hopefully you put R of T into Y sub 1, D of T into Y sub 2, and you're just able to use the variables button, Y sub 1 and Y sub 2, to do these calculations. Don't write out R of T every time. Okay. Better chance of making a mistake and just takes longer. So, math 9, 0 to 8 of Y sub 1 dx equals blank. And then make sure you're going out to 3 decimal points. Okay. For part B, again, really similar, almost the exact same problem in terms of the nature of the problem, which is the amount of water in the pipe increasing or decreasing? This really just has to deal with the rate at which water is going in versus the rate at which water is leaving. If there's more water coming in than leaving, then obviously this is going to be an increase in amount. If there's more water leaving than entering, then there's going to be a decrease in the amount. And so we can compare those specifically at t equals 3 hours by just plugging in r equals 3 or y1 of 3 and subtracting that from d of 3 or y2 of 3. And if that answer is negative, which it is, that means that d of 3 is larger, and therefore there is more water leaving the pipe, and so the amount of water in the pipe is decreasing. All right, if this was positive, it would just be opposite. But there's your explanation, a big part of this problem. I noticed that some guys on their solutions weren't writing out these solutions fully or really weren't sure how to word this. So pay attention to these, right? These are really good models. This is the exact scoring guideline that you would have to get full credit, okay? And also just notice that the justifications aren't long. They're to the point and they have all the necessary pieces, but they're not long and sort of like a paragraph or anything. They're just one sentence, very quick, very to the point. And so just kind of keep that in mind, okay? All right, part C. At what time t from 0 to 8 is the amount of water in the pipe a minimum? Okay, so we've got a little bit of a new piece here to this problem than we did for the banana problem. So I mentioned this in the last video, though, about how we might have to create an accumulation function and find its minimum value, right? And so we know that finding minimums means that you're going to be taking a derivative of a function and setting it equal to 0 and solving and then figuring out, which one of those values might give you the lowest amount. So the very first thing you need to do with this problem is create your accumulation function. And that means for the entire scenario, not just how much water is going in or how much water is leaving, but for the whole thing, right? So as water is flowing in and leaving at the same time, how much water is in the pipe, all right? And so if the very first thing we think about, hey, there's that initial value that came in, right? There's that 30. At t equals 0, I know I already have 30 cubic feet of water. Think of it this way. If you went from 0 to 0 on your integral, right? This whole integral will be 0 because you're going from one value to the same value. And then at t equals 0, because that's what we're replacing t with, there will only be 30 cubic feet of water. So that matches up. That needs to happen. If you didn't have this 30 out here, you'd be telling me that at t equals 0, there was no water in the pipe, which is not true for this scenario. So 30 needs to be there. So the 30 plus, and then we've got our accumulation. Okay, so from 0, which is where I want to start, to any time t. I want to keep this variable because I don't know what time the amount of water is at a minimum. So that's what I'm actually solving for. I'm actually going to be solving for t itself. Inside of the integral, this is very important, right? I've got r of x minus d of x. R of x minus d of x shows up in part B a little bit too, right? We replaced x with 3 because we were specifically looking at 3. But this is going to tell me exactly how much water is going in or staying in the pipe, right? The rate at which water is staying in the pipe. Because if I take the rate at which it's going in and subtract it from the rate at which it's leaving, that's going to, again, tell me the rate at which water is staying in the pipe. So how much water is in the pipe? Well, I want to take the integral of that rate from 0 to some time value. So this is my accumulation function. If you replace t with any value from 0 to 8, it would tell you exactly how many cubic feet of water are in the pipe at any point in time from 0 to 8. But the question is asking us to find a minimum of the amount of water. So if this is the amount of water, this is a function. You can call this, f of x or whatever it is, equals 30 plus the integral here. In order to find its minimum, we need to take its derivative. Well, it doesn't show you here a whole lot, right? I'm going to try and draw it here with the pen. Again, excuse the pen if it's a little clunky. So if I took d of dx of this function, right, I'd be taking a derivative of, first thing I hit is 30. So the derivative of 30 is just 0. So that goes away, right? And then the next part is an integral. Well, I know the derivative of an integral, and excuse me, I want to switch this. This should be d of dt, right? Because I want to solve for t, not x. So d of dt of this integral. Well, the derivative of an integral, there's your second fundamental theorem of calculus. I said that was going to come in, right? What do we know about taking derivatives of integrals, especially if this is just an easy variable, x to the first, t to the first? I'm just going to replace this variable with t and this variable with t. So what do I get? R of t minus d of t. That's really easy, right? Because in your calculators, now you can do a couple of things. You can create a third function in y3 that is y1 minus y2. And if you did that, you would only graph y3, so unhighlight the equal signs on y1 and y2. Graph y of 3, which is y sub 1 minus y sub 2, or r of t minus d of t, and find the x-intercept in between 0 and 8. So you can change your window, right, your x value from 0 to 8, because that's all I'm worried about. If you were to do that graph, and again, at this point, I would encourage you to pause the video and just get that set up and try that before you kind of move on to the explanation of the full answer. Okay, so if you were to graph and you were to find the x-intercepts, you would notice that happens directly at 0, and then this long drawn-out number, right, 3.27. So that's at t equals almost 3 hours. And so now we've got a couple of candidates. Remember, I keep telling you about this idea of a candidate, right? Because there's a couple of things that are possible. Number one, where are your x-intercepts of your derivative? That happens. It does happen at 0. It also happens at 3.27. And the other thing you need to consider are your endpoints. A lot of people miss this on the work that they sent in for the last problem. All right, even though I've said it in the video a couple times, you have to check your endpoints, please. So at t equals 0 is a candidate, at 3.271 is a candidate, and then t equals 8 is a candidate, great, because those are your endpoints. We need to then plug these values back into your accumulation function that you created. All right, so a lot depends on creating this accumulation function correctly. All right, so I take all these values individually, plug them in for t, and see what happens. You can see that at t equals 0, it's 30. We already knew that, so that one's not too bad. The other ones you will have to do on your calculator, right? So they get 27.964 and 48.543. You're going to have to use your calculator and just math 9, and just do this integral out, okay? So the integral of 30 plus 0 to 3.272 of y sub 1 minus y sub 2, and then you should get 27, and then do it for 8 as well, and then you should get 48. Remember, we're looking for a minimum, so we're just trying to find the smallest output here, and that is definitely 27.965. So my answer is the amount of water in a pipe is at a minimum at time t equals 3.27. Okay, there you go. All right, last part of the problem. Always trying to throw a curveball at you, but this one, again, if you just kind of work through it and think about exactly what's happening, visualization in your mind, hopefully it wasn't too bad. So what I know is that I've got this pipe. It can only hold 50 cubic feet of water. If it goes above 50 feet, 51 cubic feet, whatever it might be, it's going to start overflowing, right? So start thinking about, again, visualization. It's raining outside. You've got this gutter. The gutter can no longer hold the water that is coming in because it's not leaving enough. And so the gutter starts overflowing, right? You start seeing it sort of pour out in dumps, like it's dumping over the gutter. And so what I know is that when that happens, there are at least 50 cubic feet of water in the pipe. Okay. So it also tells me that this continues to happen after the 8 hours. All right. So after 8 hours, it's still raining. There's a lot of water still going in, and the rates from the beginning still hold true. All right. So R sub t and D sub t are still valid after 8 hours. We need to write, but we don't need to solve. All right. So don't solve if you don't have to, because that's a common mistake, people trying to solve when they don't have to, specifically when they're told not to solve. An equation involving one or more integrals. So again, I know my answer is going to have an integral in it. And in this case, if I involve an integral, it's probably an accumulation function, right? That gives the time W. So they're giving you a variable to use when the pipe will begin to overflow. So if I come down to my answer here, I'll just dissect it a little bit. Number one, I know that R of t minus D of t told me the rate of water that's in the pipe. So that's going to be part of it, because that tells me the whole scenario, not just how much is going in or leaving, but the whole thing. And then I know I have that 30 plus out in front. I still need that because that's still there. I'm starting at t equals 0 because that's really the only thing I know is happening is at t equals 0, there's 30. And then here's your time W that you're trying to solve for. All right. That's what they give you this up here. We replace this t with a w here because that's what that variable they wanted us to use. And then finally, this is the accumulation function. If I want to know the time w at which that equals 50 cubic feet of water, well, then I would set it equal to 50, right? This tells me exactly how much. This whole integral tells me how many cubic feet of water are in the pipe at any given time. Well, if I need it to equal 50 cubic feet, I'm going to set this accumulation function equal to 50. We could try and solve for this if you really wanted to, but it would take some work. That's why it doesn't ask you to solve it, just set it up. All right, so there's your setup. All right, guys, I hope this was helpful. Please check into Google Doc. Email me if you have questions. Again, if you want a video chat, I'll be around. And let me know how I can help. Have a great day.